Hello everyone, Victor is here, and in this video I want to talk about the aromatic compounds and the phenomenon of aromaticity. So what exactly is aromatic? In hint, it has nothing to do with the smell, and as a matter of fact, many organic compounds actually do have quite an unpleasant smell. So to qualify as an aromatic compound, the molecule needs to fit the following four criteria. First, the molecule must be cyclic, which means we're looking for molecules with rings in them. For instance, the first two molecules over here that I have in green are cyclic, while the other two that I have over here in pink, they're not cyclic. The molecule must be planar, or in other words, the molecule must be flat. The molecule also must be fully conjugated. This means that each atom in the cycle needs to be able to participate in resonance. Thus, each atom must be either sp2 or sp hybridized. These two requirements are intertwined, and if the cycle is fully conjugated, it will always be planar. So, for instance, here I have a couple of molecules. The first one, benzene, over here, is a fully conjugated planar species, as each atom of this molecule is in fact sp2 hybridized. The second molecule here, this one, is not fully conjugated, because we have a couple of sp3 hybridized atoms which cannot participate in resonance. Thus, the second molecule will not fit the criteria, as it's neither fully conjugated nor is it flat. The second molecule actually exists in sort of like a boat-like shape, and I encourage you to make a molecular model and see that for yourself. Finally, the last rule is all about the number of electrons in the pi system. This rule is also known as the Huckel's rule, named after Erich Huckel, the German theoretical physicist who's made a large contribution to the molecular orbital theory and the conjugated pi systems. The number of electrons in the pi system must fit the 4n+2 equation, where n is a whole positive real number. Now, here is something very important you must remember. Repeat after me. The number n does not correspond to anything in the molecule, so don't try to find the n in the molecule. The rule derived empirically from the molecular orbital theory, so don't try to make sense of it, well, at least for right now. We'll talk about the molecular orbitals of aromatic compounds in a different video, so for now, it's just a rule that you have to memorize. So, for instance, in benzene molecule we have 6 pi electrons. If we try to solve this equation 4n+2 equals 6, for the n term, we get n equals 1 right over here. So, since we get a whole positive number, benzene fits the rule just fine. So these are the criteria for the aromaticity. Thus, if a molecule fits all 4 of those criteria over here, it is going to be called aromatic. I want to come back to our electron count for a moment here, and I want to emphasize that we only include the electrons in the pi bonds and p orbitals in this calculation. So all other electrons are completely irrelevant. We're not going to include the electrons in the sigma bonds, like for instance CH bonds that we have over here, or any other electrons that may be outside of our ring or anything like that. So let's look a little closer at which electrons we actually include and which electrons are not important to us. As I've mentioned, we want to include the electrons in the pi bonds. So for instance, here in benzene and naphthalene molecules, we have the case where in the benzene I'm going to have 6 electrons. In the case of the naphthalene molecule, we have 10 electrons, 2 for each pi bond, both of which do fit the 4n+2 formula, giving us n equals 1 in the case of the benzene and n equals 2 in the case of the naphthalene. But these are just simple examples, of course. The reality is a little bit more interesting, and we are going to have other types of molecules that we see. For instance, we can have molecules with heteroatoms. Let's say we look at these 3 molecules here. I have pyridine, I have pyrrole, and I have furan over here. Each of these molecules have pi bonds and the heteroatoms with electron pairs. And a quick reminder, a heteroatom in organic chemistry is anything that is not a carbon. So we count the pi bonds. Alright, we know that. What are we going to do with our electrons on the heteroatoms though? Do we just skip them? Do we include them? And if we do include them, then do we include all of them or just some of them? Well, as always, the answer is it depends. Here is how these molecules look in 3D. And here is an important observation we can do from these diagrams. If an atom already has a pi bond, like the nitrogen in the case of pyridine over here, we cannot use its electrons in the conjugated system. This is because those spare electrons, those non-bonding electrons, are sitting on the orthogonal orbital over here, which is at 90 degrees to our plane of conjugation, which is right there. If the element does not have a pi bond, then we can use up to one electron pair on that atom. So for instance, the nitrogen atom in pyrrole over here has one electron pair, and since we do not have a pi bond on that atom as is, we can see there are just a couple of single bonds. We can put those electrons into a p orbital, making a nice p orbital like that, and include those electrons in the overall conjugation. However, in the case of the furan, the oxygen has two electron pairs. So we have one electron pair and the second electron pair. And well, since we can only put one electron pair in an orbital, we can only have one of those in the p orbital, which is going to be a part of the conjugated system. So one electron pair can sit on the p orbital, but the other electron pair must be on the hybridized sp2 orbital. Thus, if an element has more than one electron pair, you can only use one of those for the purposes of resonance and the aromatic conjugation. This way, the electrons on the nitrogen atom in pyridine are not included. We call those electrons localized, as those electrons are localized on the nitrogen and are not participating in the resonance. The electrons on the nitrogen in the pyrrole, these electrons over here, they are included in the resonance conjugation, and we call those electrons delocalized, as they are part of the resonance. And finally, in the case of the oxygen and furane, we have one localized electron pair, let's say it's going to be this one, which is not included in resonance, and we have another delocalized electron pair over here, which is included in resonance. Thus, each of these molecules has 6 electrons in the pi system, and all of these molecules, they do fit the Huckel's rule so far. We can also see cases in which our atoms in the ring are charged. So for instance, we have a cyclopentadienyl ion over here, or we can say it's a cyclopentadienyl anion because it's negatively charged. And we have a tropylium cation over here, a 7-membered ring with a plus. We'll treat carbanions, like what we have over here in the cyclopentadienyl ion, exactly like heteroatoms. So the electron pair, if that atom does not have a double bond already, can be used as a part of our resonance system. In the case of the carbocations, like what I have over here in the tropylium ion, a charge is the result of the empty p orbital. And since the empty p orbital is next to a pi bond, like in this case, it can also be included in resonance. However, the empty p orbital, it doesn't have any electrons. That's why we're not going to include any electrons for our count. Thus, we get 6 and 6 in these two examples as well. Oh, and by the way, all molecules on this page are fully aromatic, since they all fit the 4 rules of aromaticity that I have described a moment ago. But what happens if we break any of those rules? So here are my rules again. And if molecule fits all 4 rules, it is going to be considered aromatic. If we break any of the first 3 rules, the molecule is non-aromatic. Therefore, it is really important to check the rules in order, because if we break one of the first 3 rules, then it's completely irrelevant how many electrons you have in the molecule. This is a very common mistake I see many students make. They jump right away into the electron counting and completely ignore the rest of the requirements. Be careful with those. Your instructor will absolutely give you those examples on the exam that may have all the necessary electrons but will break one of the first 3 rules. And if my years of teaching organic chemistry count for anything, I am willing to bet that a lot of students will get caught by that in your class. Many instructors, however, will tell you that we can assume the planarity, which means that the requirement number 2 will be true for all molecules in the set, or at least will count them as such. In that case, you'll still need to check that the molecule is indeed cyclic and fully conjugated before you do any electron counting. Finally, if we fit all the criteria but the electron count fits the 4N formula instead of 4N plus 2, it's an anti-aromatic compound. And notice that anti-aromatic and non-aromatic are not the same thing. Aromatic compounds exist an abnormal stability compared to their open chain or acyclic versions. So being an aromatic molecule is absolutely awesome. Molecules will typically do whatever it takes to become aromatic or to maintain aromaticity. Aromatic conjugation also gives several unique chemical properties that we do not see in other types of molecules. Anti-aromatic molecules are, on contrary, extremely unstable. Thus, being anti-aromatic compound kinda sucks and it's extremely unfavorable. As a matter of fact, the vast majority of anti-aromatic compounds are too unstable to even be isolated or characterized via normal chemical tests, so molecules will do whatever it takes not to be an anti-aromatic compound. In the meantime, the non-aromatic compounds, well, those are neither more nor less stable than their open chain versions, and in other words, being non-aromatic is nothing special. It's just a regular molecule, and unlike aromatic compounds, non-aromatic compounds, they don't have any special chemical properties either. So let's check out some examples here. Like in the most typical exam scenarios, we're going to assume the planarity of each of those molecules, whether it's true or not in reality. The first thing that I'm going to pay attention to that in my first molecule I have sulfur. Sulfur has 2 electron pairs on it, so I'm going to indicate that for myself just to make sure I don't forget about those. Then I also remember that as a heteroatom that does not currently have a pi bond on it, we can only use 1 electron pair. So let's say this electron pair is going to be localized, while that one is going to be delocalized. So that means that now I'm going to include the top electron pair in my count, and I'm not going to include the bottom one. Then, counting the electrons on my pi bonds, I have 2 and 2 electrons here, plus 2 more electrons from the sulfur. This molecule is obviously cyclic. I said we can assume planarity. It is fully conjugated. It has 6 electrons, so that is an aromatic molecule. In the case of number 2, the molecule is obviously cyclic. But we have a problem with the fully conjugated system here, because what I'm seeing over here, this atom, that is an sp3 hybridized atom. And in order to be able to do the full cyclic conjugation, I need to have all of my atoms to be at least sp2 hybridized. So this one is sp2, this one, this, and throughout the molecule, everything is sp2. But this place is a hard stop. So while my molecule can do resonance throughout the green part of the molecule, it cannot do the resonance through the pink part of the molecule. And since we cannot combine that into a full cycle, that is not going to be fully conjugated. And since it breaks one of the first 3 rules, this molecule is going to be non-aromatic. Alright, so for number 3, I see that the molecule is cyclic. I see that every atom over here is in fact sp2 hybridized, so I don't have any problem with the full conjugation here. So next I'm going to look how many electrons I have. So I've got 2, 2, 2, 2, 2, and 2 for each pi bond. If I combine all of them, that is 2 by 6. So 2 by 6. That gives me 12 electrons. And if I try to fit 12 electrons into a 4n plus 2 formula, well, I'm going to have a little bit of a problem because I'm going to get n equals 10 over 4 or 5/2, which does not give me a whole number. Instead, what I can do, I can say 12 electrons equals 4n, and then my n is going to be equal to 3, and that is going to be an anti-aromatic molecule because it fits a 4n rule instead of a 4n plus 2 when it comes to electron count. So that is an anti-aromatic molecule over here. Alright, next one is my number 4. So molecule 4 is obviously a cyclic molecule. It's a very small cycle, but it is still a cycle. Next, I'm seeing that I have 2 atoms of the pi bond, and I have a carbocation over here. And carbocations are sp2 hybridized species, so I don't have any troubles with the full conjugation over here, and I can use my carbocation in resonance. Next thing, I'm going to count my electrons. Well, I do have 2 electrons on the pi bond, and I have 0 electrons sitting on my carbocation. And this is one of the things that can be a little bit tricky because 4n plus 2 equals 2 gives me n equals 0, and that is a true value for n as well. We can have n equals 0. It doesn't have to be 1, 2, 3, 4, etc. It can be 0 as well. So in this case, we do fit the 4n plus 2 formula because 0 is a whole positive integer, which means that this molecule is aromatic. Next one is number 5. So for the number 5, again, I have electron pairs on the oxygen, which I'm going to indicate right away so I don't forget about those. And then I'm also going to instantly notice that I again have an sp3 hybridized atom over here, which means that I am going to have a lot of troubles doing the cyclic conjugation in this molecule. So I have sp2 here, 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 and here, but I have a hard stop in the form of the sp3 hybridized atom, so since I cannot have cyclically conjugated molecule, it is going to be a non-aromatic molecule as well, just like an example above it, example number 2. Example number 6 can be a little bit tricky, because, well, it is obviously a cyclic molecule. I said that we can assume planarity, so we can imagine that this molecule is flat, but then when it comes to the number of electrons, it is kind of tricky, because first of all, I have a couple of sp hybridized atoms. The rest of my molecule is sp2 hybridized, so I do not have any troubles with that part. So when it comes to sp hybridization and a triple bond that I have right in the middle over here, we know that for the triple bond, I have my atoms, so I'll draw my carbon and sigma bond there, have one pi bond in one plane, so I'll draw it like that, but we then have another pi bond in the perpendicular plane, something like that, which means that only one of those pi bonds can actually be a part of the conjugation because the other pi bond is going to be perpendicular to that plane of conjugation. So if, let's say, the pink one is in the plane of conjugation with the rest of my sp2 hybridized atoms and the rest of my pi bonds, the green one is going to be at 90 degrees. So from the triple bond in this case, I am only going to count one pi bond, which means that I only count 2 electrons here, and the other 2 electrons that I have on the other pi bond are not going to be a part of my count here. So now if I add the rest electrons from the rest of my pi bonds, I have 2, 2, 2, 2, and 2 here. So overall I have 6 by 2, giving me 12 electrons, and that is a very similar situation that I have in the example 3, so that is also going to give me an anti-aromatic compound. Number 7. This is another classic example that I'm pretty sure that you are going to see on the exam as well, because this molecule, it is obviously a cyclic molecule. Every atom is sp2 hybridized, so we don't have any problems with the conjugation here, and this one has 2 electrons on one pi bond and 2 electrons on the other pi bond. So 2 plus 2 gives me 4 electrons. So this one is actually the smallest anti-aromatic molecule that you can have, and this molecule is so unstable that we couldn't synthesize anything even close to that in a free form, so that thing is just a theoretical molecule, it doesn't even exist. But that is a classic example of anti-aromaticity, so I'm pretty sure you're going to see it on the next quiz or the next exam or homework or something of that sort. Now, number 8, that looks big and scary. This molecule is called phenanthren, and if we look carefully at this molecule, well, it is obviously cyclic, although it kind of looks like a little bit of a honeycomb. Looking at all of my atoms, I can see that all the atoms throughout this molecule, all the carbon atoms that is, they are sp2 hybridized. So if I really want, I can, in fact, draw a full cycle throughout the entire molecule like that. Now, I'm going to count all of my electrons, so I have 2 electrons for each pi bond that I have in this molecule, and the overall number of pi bonds here is going to be 7, so 7 by 2 gives me 14 electrons, and that feeds the 4n plus 2 formula if n equals 3. So while you have probably heard that organic chemistry does not have much mathematics involved in it, well, occasionally we are going to crack a few numbers here and there just to keep you in shape. So based on our rules, compound 8 is aromatic. And finally, compound number 9, while that molecule might look like a cyclic compound just because it's joined in this way, we actually do not have a bond between oxygen and carbon over here. So that compound is, in fact, an acyclic or open chain molecule. And since it violates the very first rule in the criteria of aromaticity, that molecule is going to be non-aromatic. So what do you guys think about the aromatic compounds? Would you like to go through some more examples and maybe some more tricky questions? Let me know in the comments below. Also, if you like this video, give it a like and make sure to subscribe and enable the notifications so you don't miss any of my future tutorials. And I'll see you in the next video.